Hi everybody. Today we're going to do a demo. The demo is going to be about wind farm animation. The problem definition is the following. Wind turbines and wind farms are all over the news. They're all over the papers and in magazines. And what I wanted to do was to be able to build myself my own wind farm. And I wanted to do this on my desktop without having to buy expensive software and just use MATLAB to animate this. So the first step that we need to do is we need to define what the blade cross section looks like. Okay, so that the blades are the most important part of your wind turbines. So as far as the 3D geometry of the wind turbine is concerned, all the parts are easy to model except for the blade, and we want the blades to be interesting enough for our animation. So the cross section that you see here is the NACA 0015 basic thickness form. So let me explain this a little bit more. NACA stands for the National Advisory Committee on Aeronautics. So this was an organization which was the predecessor to NASA, and they did a lot of work on wing sections, especially in the 40s. During the war, there was a need for improving the design of wing sections, and so um, these folks, they did a fantastic job in doing a lot of experiments and testing, and most of the wing sections that you find out there have been in one way or the other influenced by the work of these guys. What we're going to do today is use one of their wing sections that is there in this particular book. I actually took this from this book. This is a theory of wing sections. It's an old book, I think in the 40s. It was published for the first time. Very nice book. You want to go through it if you really want to get a good idea of what the theory behind wing sections is. And what you see here is that I have chosen the z-axis and the x-axis around which I will be defining my cross section. So you can see that c is the chord length. For all practical purposes, I'll assume that c is equal to 1. And you see that as x varies from 0 to 100%, which is basically varying from 0 to 1, you'll find that z varies along these positive values, basically goes up and then comes down. What I have not done here is I have not defined the negative values, but the negative values are just a mirror reflection of the positive values. Okay, so we're going to take that into account when we do the modeling. The next thing we want to do is make the blade more interesting. So we've defined the cross section, but we now need to define what the profile of this blade looks like along the y-axis. So this is what I'm going to do. I'm going to first split my blade into three parts. There'll be three segments that I really want to change the cross section area. What I want to do is that from the y-axis value from 1 to 100, I want the cross section to vary from a scale of 1 1, which is again along the z and the x-axis, to 2 2. I want to double it, and then from 100 to 300 I want to half it, and then from 300 to 1000 I want to gradually decrease it, again half it from 1 1 to 0.5 0.5. Okay, so this is the kind of scaling that I would like to see. And if you try to visualize it, this is basically what the wing this blade is going to look like. Additionally, I would like to make this blade look more realistic, and to do that, what I'll do is that I will have a twist variation. From 1 to 100, I would like the twist variation to go from 60 degrees to 30 degrees, and then from 100 to 300, I would like it to vary gradually from 30 to 0, and then I would like a twist along the z-axis from 300 to 1000 to get the sharp edge towards the very end. Right. Key thing to keep in mind that 0,00 is the point that remains invariant under translations and rotations. All right, so once we have designed the blade, we need to assemble the system. And what we're going to do is basically take these blades, put them within a circular radius of 80 units. And we're going to place them 120 degrees apart. Okay, and these coordinates over here I've obtained by taking a 80 unit circle and just calculating what those coordinates will be at 120 degrees. The hub will be an ellipsoid, an assumption that we're making, and AB will be both 105 units. C will be the one that is scaled up by a factor of 4, so that we obtain that oblong shape that is so much characteristic of the hubs that see out there. To get the blades to be facing us, we need to translate the hub by 140 units backwards into the into the z-axis, and the tower. What we'll do is simply model it as a 1700 unit long cone. Basically, it's going to be a cross section that varies from 1 to 1.2 1.2. Okay, and we're going to place the tower just behind the blades at these coordinates. All right. So the critical thing to keep in mind over here is that when you're building a very complex scene, it is very important for you to get an idea of what the 3D geometry is like. And once you have that idea written down or have it in your head, then translating that into a scene becomes a lot easier. Okay. So let's go and try to model this in VRML. All right, so we have the VRealm Builder Editor open over here, and to realize this complex shape, what we're going to do is basically go ahead and use a new kind of a node. So let's first go ahead and click on a new world node here. Let's go to nodes, click on insert, click on geometry, and what I'm going to do today is use the extrusion node. So the extrusion node is a very special kind of a node in the sense that if you have a 3D geometry, if you have a 3D body and you know how the cross section or the slice of that body looks along a particular direction, if you can define that, then it is possible for you to pretty much define what the 3D shape looks like. And that is precisely what this extrusion node does, is that if you can define the cross section as a function of the direction, then it is possible for you to define that particular 3D shape. And that's exactly what we have for the definition of the blade geometry in our problem. All right. So another thing to keep in mind is that today we're going to push the limits of this particular editor. What do I mean by that? I mean that I'm actually going to go outside this editor and modify the WRL file to be able to realize my complex shape. Okay. So let me go ahead and save this. I'm going to save this as windturbine.wrl. Okay, and if I click on the extrusion node, I see that this is the cross section. So the cross section is pretty much along the x and the z directions, and the spine, which is the direction along which this cross section is varying, is along the y-axis. Okay, and you can see that this, the editor allows you to define simple shapes or simple geometries, but we need something more complex. Okay, and to do that, we need to go outside the editor. And this is something that you'll encounter with all editors out there, that there will always be some limitations to what the editor can do. All right, so let's go ahead and close this, and let's save this. Let's go to the file over here, and let's open this up in WordPad. Okay, so this is the cross section that we have, which is basically a square. Okay, and I am going to take the cross section data of the wing section, which I have copied onto the notepad file over here. I'm going to copy this. I'm going to delete this. Okay, I'm going to paste it. Okay, the next thing I'm going to do is that I know that the spine, which is the length of this particular profile, varies from 0 to 1000. Note that these coordinates, this is the y-axis over here, and this is the x and the z-axis. Okay, so let me go ahead and save that. Let me go back to my file over here and open it. If I double click on it, you can clearly see that this has created some kind of a 3D body here. If I click on model, and if I rotate this, I can see that I have the cross section that I needed. Okay, and this cross section is originally pointed along the x and the z direction. Okay, because the z-axis is pointing towards you, x-axis is to the right, and the y-axis is pointing upwards. Okay, so this is the cross section that we wanted. Okay, so the next thing I'm going to do is basically change the profile of this cross section. So I'm going to go ahead and go to the spine section over here, and I'm going to say that there are 3 cross sections that I'm really interested in. Okay, and then I have another cross section that varies from 0 to 300 to 0. Okay, the important thing to keep in mind is that I want the cross section to first increase. I want it to double. Okay, I want it to double at 0, 100, 0, and then I want it to come down to 1, 1. I want it to vary 1, 1 to at 300, and then I want it to decrease to 0.5, 0.5, 0.5 when you go all the way to 1000. Okay, so let me go ahead and save that. Let me close this because I have to open up the WRL file again. Let me double click on that, and you can see that I have defined a complex shape. Okay, so from 1 to 300, the scale increases from 1 to 2, and then from 100 to 300, I bring it back to 1, 1, and then from 300 to 1000, I bring it to 0.5, 0.5. So I have kind of defined a pretty complex shape if you see over here. All right. Again, the extrusion node is a very good node to use if you know pretty much how the cross-section area varies along a particular direction, which is the spine over here. All right. All right. So let me save that and close this. And now what I need to do is define the twist that is there in our blade geometry. So we know that initially we have to start at 60 degrees, and to do that, let me go ahead and change this to 1. The twist is happening along the y-axis. 60 degrees is pi by 3, so that's 1.04. And I know that I need to vary it from 1 to 100, from 60 to 30. So I'll bring this to 0, make that half of that. And then I need to do some more variations here. And I need to vary that gradually to 0 from 100 to 300. Okay, and then from 300 to 1000, I do a twist along the z-axis to get the sharp edge that I need. Okay, so let me go ahead and save that, and let me go back to the wind turbine here and click on that. And if I click on model and move this, I can see that I'm able to define a pretty complex geometry by putting this twist in the 3D geometry description itself.